Okay, so today is lecture 9, and I'll continue to talk about Grassmannians. We started last time. I presented some ad hoc construction of the cluster structure on the coordinate ring of the Grassmannian, and now I give some more context to this construction. In order to motivate it, I start from analogy or maybe recollection. So recall what we had for Grassmannian 2n. In this case, we considered cluster structure starting from triangulation. So we take any polygon prepared to this lecture. I used to write several octagons. So let me write it again. We take some polygon convex n-gon. We take its triangulation. And then we assign cluster monomial to any edge or diagonal in this triangulation. Of course, I'm not going to say that we get exactly this structure later. But what we could expect, we could see an analog of some reformulation of the structure. And recall how we construct, so let me copy this figure. And recall how we constructed the quiver. We put a vertex inside of each diagonal or side, and then connect them. In each triangle, we draw some small triangle with clockwise orientation. Sorry, I didn't prepare this picture, so it takes some small time to draw. Also here. And the orientations are clock side inside of each triangle. This is more close to what we could expect to generalize, but there is one more combinatorial language which we can actually use for drawing quivers. Namely, it was the language of bipartite graphs. Indeed, we can instead of this, also bipartite graph. Maybe erase the quiver. this bipartite graph will be dual to the quiver. So this is why it is not very convenient to draw them on the same picture. Sorry, this is wrong. So now to each, before each variable correspond to the side or diagonal of the triangulation, now each variable will correspond to the face of this bipartite graph, dual graph dual to the quiver. And similar to the situation as we had with networks when before, we have bounded and unbounded faces. Bounded faces correspond to unfrozen variables, and unbounded faces will correspond to frozen variables. As I said, this graph is bipartite, so for structure in each triangle, we draw a vertex which is black, and vertices of the original triangle are white. Original polygon are white. Now, if you want to reconstruct the quiver, then as I said, the vertices are faces for the bipartite graph, and the definition and the arrows goes defined like this: that we should go clock. Yes, I forgot what was my favorite rule. Clockwise, counterclockwise around the black edges. Maybe I just look to the some of my old lectures, maybe this one, and see. So the edges goes clockwise around the black vertices. So we will have disagreement between this and that. No, everything agrees. So we have H like this, and so on. This can, so clockwise. And this is, it appears this combinatorics of the dual graph, of the bipartite graph, is quite generic. It is applied in many, I'm not going to say that in all cluster algebra stories, all cluster algebra examples related to Lie theory, but in main examples for the type A, I would say so. In particular, it's applied to Grassmann. Actually, it is sufficient to work with bipartite graphs, but quite often people use a bit more general option of the notion of the playback graphs, which I'm not going to define now. Definition. Playback graph is a planar bipolar graph. Let me remark that Plabic. Okay, postpone this remark. There are following. Okay, we will consider today Plabic graphs will be embedded to the disk. It will mean that it has some numbers, say, and boundary vertices, and equal to 0, which belongs to the boundary of the disk. And we will usually label them. And other vertices are called internal. And there is also assumption which we will not always use, but for the record, I put it. Boundary vertices have degree 1.
And they are one color, yes? Or not necessary?
Theoretically speaking, not necessary, but in examples which will, I mean, I'm going to tell you 2 stories about Plabic graphs, and in one of them it will be necessary and another not. Okay?
Okay.
Up to now I didn't assume this, but you will see. In story which from which I start, this is not necessary, and theoretically speaking, one can think that boundary vertices are not colored. Okay, example. I'll give you 2 examples. First example, this. You see, now instead of disk we have octagon, but who cares? I delete this internal edges. This is bicolored graph, Plabic. This is Plabic graph. And If you want something more simple, then one can just draw a circle and draw something like this. Sorry. Okay. We will use bicolor graph up to some equivalence. And equivalence is given in terms of certain moves. Now let me define this move. There will be 4 types of moves. First one is like this. We have essentially a figure like this. And move it to a figure of the same type. But the only difference is the change of the coloring of the vertices. So here it will be opposite. So this move applies for foregone face with vertices degree 3. This is the most important move, which has number 1. Move number 2 is the following. Assume that we have 2 vertices of the same color, which are connected by H. The color can be black, or it can be white. So I draw now. I draw with a bit more care. Then you can just glue these 2 vertices together. What does it mean? You erase this here, this. Oh, sorry, I don't like this picture. Let me use the second one. You copy. Then you delete all this and move them together. And you do the same for the black coloring.
And we don't get 2 cycles this way.
In principle, we can obtain a cycle for this one. Let me double check it. So is it assumed here that there is only one edge between these two? Let me think. I think no assumption.
Okay, but
And
a vertical which is connected with both of these verticals, this gluing give us a two cycle, yes?
yes. For Plabby graph, there's no assumptions. There's no two cycles. Okay, so this is move 2. I follow some reference in the number of the moves, but don't consider this very seriously. Actually, I follow 2 references, and the number differs. Okay, now
sorry.
Yes.
May I ask if you have in this case 2 vertices and one is on the boundary, we should move it from the boundary when we glue.
No. If vertex on the boundary, it is somehow fixed here. We should move vertex which is outside of the boundary.
But then we will have vertices on boundary with more than 1 degree. No.
If you assume these conditions, then it means that you cannot. In this case, you cannot contract the corresponding edge. Okay.
Okay. We just can't do this move to vertex which is on boundary. Okay.
If we can, then we can. Okay. Now one more move, which means that we can, if we have a vertex of the degree 2, then we can just contract it. Okay. And again, this works for any color. Okay, and last, 4th move. Is exactly works with the 2 cycles. Assume that we have 2 cycles with boundaries with the vertices of the different color. So one vertex is black and another vertex is white. And then the move is just delete sorry, let me think. I think just delete the corresponding edges. And this is As I said, not by move, but by letter R, which is sense reduction. Okay, this is a list of some list of local moves. Let me give a remark. Playback graph is not necessary by bipartite. I didn't assume there is no edges which connect vertices of the same color. But it can be made bipartite using moves M2 or M3.
And the last move, if two vertices connected with odd one numbers of okay, with odd numbers of
So here can be many other edges.
no, I mean these two, like
For example, it could be edges like this.
Yes, and these edges are also we should delete. Could we delete?
I delete just two neighborhood
Okay,
edges.
so if they connected with the odd number of
Then
edges,
just one remains.
yeah, okay, thank you.
Okay. Let me think a minute. Yes, I think I'm correct. I think I'm correct. Okay, another remark. For bipartite graph, first move M1 can be restated as follows. So we take a square, take square face. In what I'm going to say, it is not necessary to face to vertices to be three-variant. This is the difference. So now vertices have, I don't know, larger valency. Then I cannot just change the color of the corresponding vertices because I will have edges which connect vertices of the same color. But what can I do? I can put here intermediate edges. intermediate vertices. And then draw the square inside. So we can copy in order to see analogy. So if I start with exactly this story, exactly this, where all these edges will be 3-valent, then this additional vertices are in fact 2-valent, and they can be contracted. But in principle, this construction, this is like surgery, if you want. I deleted this 4 edges and added such piece, which consists 4 new vertices and 8 more edges. Usually, after this surgery, one can contract something, but theoretically speaking, not. This is the definition. So one can contract or remove some vertex. Okay.
You mean that we add this transformation by definition, or it follows from previous?
It follows from previous, yes. You make this transformation, and then you made transformation inverse to then you for 3-valent case you just add this transformation. You add additional vertices here in 3-valent case.
Yes, I mean that somehow the last move is stronger than its previous version, since for previous version we could move only in case of degree 1 vertices, or
but it's not important.
Degree.
If this degree is high, you can deconstruct the edges, so you can add here some. You can decompose this edge, these vertices, using this move into 3-valent and other steps, and then apply the move.
Okay, I see. Thank you.
And this is literally what's going on here. So you first decompose and then apply this move. This restatement. So how to say this restatement, but advantage that this preserves bipartite structure. Okay. Okay, the equivalence class of the Plaby graph G is a set of Plaby graphs. Sorry, here I was wrong. It's only one arrow in one direction. is a set of Plaby graphs, set of all that can be obtained from G applying first three moves, M1, M2, and M3. At last definition, if doesn't exist graph G prime equivalent to G such that reduction move R can be applied, to G prime, then G is reduced. I'm going to say that for any reduced Plaby graph, one can assign a seed for the Grassmannian. These Plaby graphs are form a replacement for the triangulation of the convex point. Sometimes the seeds will be just equivalent, and sometimes seeds will be related by mutation. But first, I have to define the quiver. Okay, quiver. Vertices are faces for Plaby graph. And arrows I can repeat as I usually say that around the black vertex we go clockwise, around the white counterclockwise, or I can draw a picture so that if we have some arrow such that its endpoints have different color, then we have H like this. And if we have arrow where endpoints have the same color, then for both those cases, no edge, no arrow. So in construction of the quiver, only edges which connect vertices of different color matters. If we return to our picture, then what we see here, we contract the arrow, but this arrow does not, we contract the edge, but this edge doesn't correspond to any arrow, so quiver remains the same. Here, the situation actually depends on what we have on the boundaries. For example, if we here have black vertices on each boundary, then before contraction, we have one arrow here and one arrow here, and after contraction, we have 0 arrow. So actually, the arrow just cancels. If we have white arrow edges, white vertices on the boundaries, then we have no arrows in both cases. If we have one black and one white, is here. Then before deleting of the vertices, we have one arrow here, and after we also have one. We'll have one arrow up. Conclusion of all what I have, for what I just said, is the following. This could state as a proposition. Okay. Move 2 and 3 preserve the quiver. And B will correspond to move 1, and move 1, of course, is a mutation. It can be seen, for example, from this picture. So we have vertex, and before, and because we change for each edge of the corresponding face, we change the coloring of its endpoints. Therefore, we change the direction of the arrow which correspond to this edge. And one can also check that everything works nicely with the other edges, which we change. So that everything agrees with the definition of the curve mutation. I don't know, maybe it's similar for the bipartite graph case, because you have less cases to consider. Maybe it is. So if we have some playback graph, say reduced, then on its equivalent class, there will be some set of playback graphs which are obtained by moves 1, 2, and 3. Moves 2 and 3 doesn't change the quiver. Move 1 correspond to mutation. Now I have to say which playback graphs I have to consider. What is the condition on them? And it appears that these conditions can be nicely set in terms of the zigzag passes. Definition, which I hope I already gave, zigzag pass. Sometimes this is called trip. sometimes there's other terminology. Will use this terminology. The exact path is a path which moves right in black vertices and left in white vertices. Maybe a copy some suggestive picture. Before I use the zigzag passes only for Bershtein graph, but in principle one can use them even for Liebig graphs. It's clear to see that the transformation which we use M2 or M3, which transform Liebig graphs to Bershtein, they do not change significantly zigzag passes. For M3, it's clear that if we go, then we do for vertex of valence 2, zigzag path does not actually see it; it just goes directly. And for M2, for example, here we move right. So before we have zigzag path which goes like this, but after the gluing, it will go. It comes from the same edge and depart to using the same edge. So it doesn't change its orientation. It doesn't change the source and sink. Let me now show you a more difficult example, which I copied, but which I actually prepared. Choose this. Here I draw several zigzag passes. I didn't color the boundary vertices because the coloring is unique and not important for the zigzag passes because they have degree 2 or even 1. First, for example, green. I believe this color is green. I also colored a point on the boundary. Each zigzag path starts somewhere on the boundary. At least up to now, I consider such a zigzag path which starts somewhere on the boundary and should end somewhere on the boundary. So, for example, hence we have a permutation. So for any Liebig graph, give us permutation. Of boundary vertices. each, for example, in this here, we have a 7. 1, 2, 3, 4, 5, 6, 7 boundary entries. And what we see the zigzag path, which starts from 5, which it after some work ends at 4 and 1. So 5 goes to 1. Orange zigzag path, which starts at 6, which after some works ends in 2. And I also draw one more, which is the simplest one. It is the first, which starts from 1, and it ends on 3. Couldn't be so. No, it couldn't be so. Sorry. I sure this is a mistake, and I'll explain you why this couldn't be so in a minute. But you see here we should move right because it's a black vertex. Okay, we move right, and now we come to white and move left. So this is exact path. Starts from 1 and moves to 4. And one can check that all others goes like this. So definition. Grassmannian permutation Kn. Permutation is a permutation which maps any number I to I plus k mod n. And easy lemma.
Sorry, may I ask?
Yes, of course.
Is this true that we always will have like one long cycle, or it is just by accidentally in this case it appears?
This is not accidentally, but this is not true for any Plaby graph. This is only true for Plaby graphs which correspond to Grassmannian. This is why I consider this example.
Okay, thank you.
Theorem, which is due to Postnikov, who actually invented all this technique, all this combinatorics of Plaby graph. Two Plaby graphs G. Maybe it can be stated as follows: if permutation G and G prime are reduced and permutation Plaby graph G, we assign permutation, which is about pi of G. Permutations pi of G is equal to pi of G prime, then let me restate. Let G prime reduce. Then P pi of G equivalent pi of G if and only if G prime belongs to the mutation class of G. And of course, opposite. So if two Plaby graphs are related to the moves M1, M2, M3, then the permutations are the same, and this is straightforward. And of course, difficult part is the opposite. That this permutation is invariant of the mutation class of the moved class of the Plaby graph. This is what I said you something about combinatorics. I didn't say, I have to say something about algebra, about how to get the cluster, about cluster variables from this picture. And the rule actually, as before, we draw our zigzag, and for each zigzag, we look to the faces which are on the left of it. So for any zigzag, it starts somewhere on the boundary and somewhere on the boundary. So it divides the disk in two components. So let's take the components which are on the left of the zigzag. And for any face, we assign the numbers of zigzags to which components this face belongs. So for each zigzag, we can assign number of faces which are on the from the left of it. This should resemble the story which we had for double cells. In that case, we look into the zigzags which are below to the face. Now we don't have the notion below, but we have such replacement if you want. So for example, here I wrote 4, 5, 6. What does it mean? That zigzag starting at 4, at 5, and at 6, for them this face is on the left. For zigzag 6, we see here that its behavior, and 4 is on the left. For 5, we also see, and for zigzag number 4, we can actually see that if you believe me I made labeling correctly, then you can actually see that this zigzag number 4 goes, goes like this. And therefore this face also belongs to its left component. One can, let me restate it, it's in one more way. So for each zigzag Z, I assign, let me write it, the component dz, half disk. So for each face F, number of Z such that this component, this boundary component, this face F belongs to dz. one can take the union of dz over all z, which is glued by boundary, by internal edges. I mean, any edge belongs to two zigzags. We can go, which goes right or left. So we take this half discs, this disc, and glue them, gluing the corresponding edges. We obtain some surface with boundary, and there is a map from such surface to D. And it's easy to see that this map is a ramified covering. Hence, for any face, the number of its preimages is constant. So the number of zigzags and the number of preimages is exactly the number of zigzags z, such that f belongs to the corresponding dz. So remember this lemma, or maybe proposition. Corollary. Any f number of z such that f belongs to dz is constant. And look into the boundary faces. For Grassmann permutation, it's clear that this number should equal to k. If you look to the boundary faces, then you know which for which zigzags it belongs to the left of it. The zigzag should start before this face starts and end, and that's after the end of this face. So it is easy to see that it will be just k. So corollary. For Grassmann permutation, we have exactly k zigzags for any face. So for any face, we assign some zigzags with numbers e1, ek, so we can assign a Plücker coordinate d1, dk, which belongs to coordinate 3 of the perspective. This is the construction. One can look again here. So we have here draw some Plabby graph. It has quite a lot of faces, and to each face I assign 3 integer numbers from 1 to 7, which correspond to zigzags, for which this face belongs to the left. And hence, for any zigzag, for any face, I assign Plücker coordinate. There is a natural property of this assignment which should be checked. Problem. move M1 corresponds to mutation of this delta coordinates. So what does it mean that we start? Let me draw this move here. We have some Plücker coordinates on the left side, so we have some set here, set E1, E2, E3, E4, here I. And actually, after such transformation, it's quite easy to see that set of zigzags here remains the same, and here set a bit changed. So actually, this leads to three-term Plücker relation. It is easy to see. I mean, what I'm saying that we don't need to study all zigzags for this problem. If zigzag goes somewhere, does not affect any of this vertex, then it is not important for us. The only actually only 4 zigzags are important, which come to this picture. And looking to them, one can see that zigzags assigned to these faces remain the same, and set of zigzags assigned to this change slightly, and such that we have such relation. Hence, we have a map from the cluster. We have a map from cluster algebra. To the algebra of rational functions in principle on the affine cone of a Grassmannian. We can take any Plybig graph which corresponds to Grassmann permutation, assign to face variables minors, and actually doesn't depend on the choice of the initial Plybig graph, because they are related by mutations, any two Plybig graphs by the Postnikov theorem. And this mutation in terms of cluster variable corresponds exactly to mutation in terms of the Grassmann variables. And the last time I proved, or maybe stated the idea of the proof, and give a reference to be more honest, that this map is isomorphism. So theorem. Maybe the first person who proved it was Scott. This is isomorphism. Okay, other questions?
what are permutations which correspond to bipartite graphs in general? Maybe in more general a bit.
For any permutations that exist in bipartite graph. I think the answer is yes. For example, you can take the following bipartite graph.
Sorry, I understand.
It corresponds to trivial permutation.
Oh, okay. Sorry, I thought bipartite graphs corresponds to some subgroups of permutations, but I see it's different. Okay, sorry.
I mean, there's a theorem by Postnikov. Can you hear me now?
Yes.
Yes.
I mean, my computer complaining about my microphone, and I changed to iPad. I don't know. Maybe it will be not good for the video. Okay. Not good. Anyway, it remains 10 minutes, doesn't matter. So I can add here that another point. Another point that for any permutation. G such that I is equal to pi G. Okay. Now, in remaining 10 minutes, I would like to cover a completely new theme, which should remind you the following: that when we discussed algebra cells, we actually have two different stories. In one, we assign the we draw the network, and then to each phase we assign the minor using zigzags. We compute orange zigzags below. We'll look which of the orange zigzag goes below, which are green zigzag goes below, and so on. And then we assign corresponding minor. And another approach was different. To each network, we assign factorization scheme. We take the product of certain matrices, and then we compute, actually we can compute the corresponding product, and it computes and this gives us the matrix. So this is another parameterization, if you want. The matrix which we compute using the product is the matrix of paths from source to target. This we fix a point on the boundary from which we start, we fix points on the boundary in which we end, and this matrix consists of the sum of the weight of the paths from the source to the target. There are two different stories, and here I actually want to state the reason there's a story very close to what we had mentioned above. I will start, I mean, in 5 minutes or 10 minutes, or if 10 minutes, and so on. Okay. So another method, and it will use the notion of the perfect matchings. Okay, definition. Let G be a finite graph. Perfect matching. Of G is a collection of edges of G such that every vertex is collection, say, M. Every vertex is contained in precisely one edge. Of G. Another, sometimes instead of perfect matchings, people say about dimer configurations. Okay. Now let me state some result, which is some definition which is a bit more close to what we're going to say. So assume that we have a graph G, which is now assumed to be bipartite. I assume G is embedded to the disk. Now I assume that boundary vertices G are let's assume white. I will say definition. Perfect matching with boundary is collection M as above, such that any internal vertex contained precisely one edge of M. So if I will use some combinatorics, so let me denote that some number of black vertices of G, let denote by n plus k, and number of internal white vertices of G, let me denote by n, and number of boundary let me denote by n small. Then for any set I, subset of 1 to n, I can compute di is a number of perfect number of perfect matchings as with such as the boundary is consists of vertices from I. So in order to have, so if k is not equal to n, there is no honest perfect matching for the graph G. But that graph perfect matching exists only if number of white and black vertices is the same. But for graph with boundary, we have freedom, and we can take any k vertices from the boundary. We don't. We shouldn't take all of them. We just take the number which is necessary for the count. So the dfi is a sum of a perfect with boundary I, weight of the corresponding M. Let me give you an example. Just to be sure, can you still hear me? Because my computer complains.
Yes.
Okay, you don't complain. It's okay. Example. Here I didn't prepare a difficult example, so I will give you quite a simple one. Very simply. And these two vertices are black. Okay. I number the boundary vertices 1, 2, 3, 4. And also I have to put some weight to the edges in order to have more freedom if you want. Let me pick just random numbers. A, B, C, D, E. And maybe just to make the story more simple, I move this vertex to the boundary. A, B, C, D, E. Here will be F. Okay. I can color white vertices to white. Thank you. Okay. So let us compute. Delta 1, 2. What are the dimer configurations for which on the boundary we take vertices 1 and 2? Clearly, we have only one such configuration, which is like this. So this is equal to 80. Delta 1, 3. Who can suggest? Who is still listening?
It should be F and
Yeah,
A.
exactly. AF. Delta 1, 4.
A and E.
Mhm.
Can you
Delta.
please repeat why it is so?
What should this?
And delta 1, 2 and delta 1, 3.
Delta 1, 2. I take it as sum of all perfect matchings with boundary I.
Mhm.
For delta 1, 2, boundary is 1, 2, so I can consider all perfect matchings which includes 1 and 2 and doesn't include 3 and 4.
Mhm.
So I should take configuration for edges which include 1, 2 and all black vertices in this case. There is only one such configuration.
Okay, thank you.
No, this example is the only reason which I'm giving, not to make sure that it was possible to understand my definitions. Or if, of course, nothing. Okay, 2, 3 is BF. 3, 4 is what? CF. 2, 4 is, and here is the only interesting case, we have BE plus CD. We have two dimer configurations. And one can see that actually all this delta satisfy Blücher relations. And this is not coincidence. Actually, this is a general theorem, which I plan to prove, but maybe I would just give the proof in notes and problems. Theorem is that delta I satisfy. No, okay. Either all 0 or define point in Grassmann. In other words, we obtain a map from the if you want R plus new power number of edges to Grassmannian Kn, and actually it will not just Grassmannian, it will be positive Grassmannian. So the set of the subspace such as all Bruker coordinates. I think I should stop 4 minutes ago, so I will everything else which I want to add, I will let you know so next time. Questions?
So this either 0 or defined point means just the same as before, that they define point in cone, right? Or it's different?
Say defined point
In Grassmannian cone, like
if I will think what is the best way to put it, but if they exclude cases all of them are 0, they define actual point in Grassmannian because they're homogeneous coordinates. They define point in Grassmannian cone always, even if all of them are 0. It is a nice point in Grassmannian cone. I mean, not nice, not smooth, but to the point. So I can maybe I put okay. It's up to you. I can put here head and delete this. Other questions? Okay, if no questions as